Hey there guys, today we're going to start Unit 8, Notes A. In these notes we're going to talk about solutions and solubility. First, let's start with a question. What are some things that you can do in order to get sugar to dissolve in your tea? You want to make your tea sweeter, how could you do that? Well, there's several things you could do. Most of the time I hear things like heat up the tea, stir the sugar in the tea. So these are all things that are going to help with the dissolution or dissolving process, adding heat energy or chaos, also known as entropy energy, to the system. So we're going to talk about solutions and solubility, starting with some very basic definitions. First of all, a solution is a homogeneous mixture. Remember, homogeneous means it's the same consistency throughout. So to the naked eye, it's going to look the same throughout. Usually they look pretty watery, because water is a really good solvent. So the solvent would be the medium being used for dissolving, or the big liquid thing that's dissolving the other substance. The other substance that you put into it, for example, the sugar in our sweet tea, we would be putting that solute into the solvent to make the total solution. So we need to be able to identify the parts of a solution. For example, if I made salt water or aqueous sodium chloride, which would be the solute, the salt or the water? Solute would be the salt that we put in, the NaCl, whereas the water would be called the solvent. So water is the solvent, and it's also commonly used as a solvent. We actually call it the universal solvent, and then the solute would be whatever substance we're putting inside the water. In this case, salt, or in the example with the tea, it'd be the sugar, the particles that are going inside. So let's talk about dissolving. There's a fancy term for it known as dissolution. When I say dissolution, I'm really just talking about dissolving the solute in the solvent. But what are some things that actually occur when we do this? So say I take my sodium chloride and I put it into the water. The very first thing that's going to happen to that sodium chloride is the sodium ion will break apart from the chloride ion. This is a process known as dissociation. So careful, those two words sound very similar. Dissociation is literally referring to the breaking of the ionic bond, whereas dissolution is this and the next step we're about to talk about. During the dissociation process, energy has to go in to break up the bond. Remember, these atoms bonded for a reason, because it made them more stable. And so breaking up that stability is going to require an input of energy. The amount of energy required to form the solution is known as the heat of solution. How much energy has to go into the ionic bond in order to break it. Once that breakup occurs, those atoms aren't just going to, or ions I should say, aren't just going to hang out together. They're going to float away from each other, and the water particles will rush in. That's a process known as solvation, basically where the solvent comes in and interferes right after the breakup, like the friends after a real breakup between a boy and a girl. So we've got this breakup of cation and anion, and the water rushes in between. So the breakup is the dissociation, and the water rushing in between is the solvation. You put these two steps together, and you've got dissolution. And this is going to happen to every ionic compound, because all ionic compounds will dissociate in water. So question then, will this happen to covalent compounds? Is it possible to dissolve something covalent like sugar? We were just talking about dissolving sugar in the tea, right? So what would be different about this process, considering that covalent bonds do not break up in water? Only ionic bonds break up with water. Well, the only thing that's going to happen is we're just going to skip that dissociation process. It will not break up into the separate atoms because the covalent bonds won't break. But the sugar particles will still kind of move away from each other, and so you're still going to get solvation. So dissolution is just a one-step process for covalent compounds where the particles stay together, and it's a two-step process for ionic compounds because we're going to break the bond and then every little particle will run away from each other. So one step versus two steps. All right, let's go back to talking about dissolution as a whole. What is going to help this dissolving process occur? What's going to be more favorable? Well, first of all, we want energy in order to go into those ionic bonds to break them or to allow the particles to move around faster to enable solvation. So think conservation of energy. That energy has to come from somewhere. So if I have a system that's able to give off energy to the solute, then that's going to favor dissolution. The other type of energy we talked about was that stirring process and how it created all that chaos. Those particles bumping around are going to favor dissolution. And we call that something called entropy. We call that entropy. So a high entropy with lots of bumping and bouncing around is going to favor the dissolution of the solute. It's going to help things dissolve more quickly. So basically we want an input of energy. Whether that's from heat or from chaos, it's still going to favor dissolution. So what things can dissolve what other things? You may have heard that oil and water don't mix. It's a very famous example of things that will not mix. But lots of things mix in water. We can make a lot of different aqueous solutions. So what is it that determines if something will mix with another substance or not? Well, first of all, being able to be mixed together, we would call that miscible. And by the way, if you cannot mix, the prefix would be immiscible, like impossible. I can never spell immiscible. There we go. So if they can mix, they are miscible, kind of meaning mixable. And if they cannot mix, they are immiscible. So what things do mix? Well, it has to do with if they have like polarities. So if both substances are polar, then they're going to get along just fine. If both substances are nonpolar, then they'll get along just fine. But if one's polar and one's nonpolar, then it will not mix. So oil, being nonpolar, does not mix with water, which is polar. So you have to have the same polarity, both being polar or both being nonpolar, and then they will mix. All right, next thing I want to look at is how quickly we can get something to dissolve. So say we really want that sweet tea, we really want the sugar to dissolve in the tea. What are some things that we can do to make that happen even faster? So the first thing that we mentioned is we could possibly increase the temperature. You're going to get the sugar to dissolve in hot tea much faster than you would get it to dissolve in cold tea, which is why a lot of times they add sugar to the tea when it's first brewed if they want to make it into sweet tea. So as we increase the temperature, those particles are going to be moving faster. So it's going to be more energy available to go through dissociation and increasing the chaos of the system. All favorable things. The other thing I could do is agitate. So that was the idea of stirring the stirring the sugar into the tea. So if you agitate it, you're increasing the chaos of the system, which was one of our favorable processes. The last thing that you could actually do is to break up the sugar. So imagine a sugar cube versus a packet of sugar. Putting the packet of sugar is going to work much more quickly because more parts of those sugar particles are exposed to the liquid. Whereas if I had a sugar cube, I would only be able to dissolve the outside layer and then could go into the next layer and then could go into the next layer. The inside particles are not going to be exposed to the liquid and therefore wouldn't even have an opportunity to participate in the dissolution. So if you make the particle size smaller, you're actually exposing more of it to the liquid and will make that process then happen faster. So all of these things, increasing these things, will all increase your rate of dissolution, how quickly something dissolves. Let's talk about how much stuff can be dissolved now. So you may have heard of a saturated solution. What that means is the exact maximum amount of solute that you could possibly put in solution is in there. Say, for example, at room temperature, my tea can hold 10 grams of sugar. If I get exactly 10 grams in, then I have the perfectly saturated solution. It's also possible not to saturate the solution or to create an unsaturated solution. So if the solubility of the tea is 10 grams at room temperature and you only put in 5 grams, it has the potential to hold 5 more grams. So if you're under the maximum amount, then it would be unsaturated. Now, this is a little weird, but there's also a way you can hold more than the maximum amount of sugar. This is how rock candy is made, actually. So let's kind of walk through what this would look like. So let's say we have let's just go with sugar water on the idea of making rock candy. And we're at room temperature, which is about 25 degrees Celsius. And let's say it can hold 10 grams. Then you're going to heat up your water, make it boil at 100 degrees Celsius. As I increase the temperature, I'm going to increase the amount of solute that it can hold. So instead of only being able to hold 10 grams, now maybe it can hold 20 grams. No, it is not linear. So then when we go from 10 grams to 20 grams, I am still saturated because it is at a new temperature. So solubility actually depends on temperature. If I can hold 20 grams at 100 degrees Celsius, at 100 degrees Celsius, that's a saturated solution. If I can hold 10 grams at 25 degrees Celsius, at 25 degrees Celsius, if I have 10 grams, that's a saturated solution. So these are both two different types of saturated solutions that I could make. The next step in rock candy after you boil it is to cool it down. And the faster you cool it down, the better your rock candy will be. So the idea is then I drop back down to room temperature, or maybe even lower, down to 0 degrees Celsius, but the 20 grams stay in solution. So when you have more than 10 grams, when it's only supposed to hold 10 grams, or maybe even less, maybe 5 grams, and it still has 20 grams, now you have a super saturated solution. There's excess in solution. We tricked the water into holding more, and then we cooled it down too fast for it to come out of solution. Now, it will eventually come out of solution. That's where the rock candy comes from. Eventually, all the sugar that we dissolved here is going to come out of solution all the way down to the 5 grams that are allowed to be in solution. When something comes out of solution like that, we call it a precipitate. So the sugar will precipitate out of solution and create the rock candy. The idea here is that it's temporarily holding more as a supersaturated solution, but over time, or when triggered by maybe an extra crystal after it's cooled down, then you can get it to precipitate out of solution. So that's supersaturation for you. So let's define solubility. As I kind of just showed you, it is hugely dependent on temperature. So the saturated solution is when it has the exact amount as is soluble. So the solubility amount will depend on the temperature. With the examples we were just looking at, we said we could hold 10 grams at room temperature. But if you change the temperature, you change the solubility. When you have the solubility amount, you have a saturated solution. And if you have less, it's unsaturated. If you have more, it's supersaturated. So what can affect how much goes in? Well, of course, temperature. Also, what the substance is. Like we talked about miscibility. And so if a substance is polar versus non-polar, it may not be able to go into solution. So just like what it is made of, what kind of intermolecular forces exist. And then the big one we just talked about was temperature. So when we talk about solids, with the examples we've been using all day, we say that as we increase the temperature, we increase their solubility. Actually, the opposite is true for gases. Think about it for a second. Gases are already very chaotic. And so if we're adding more chaos, they're going to be even less happy about calming down and hanging out inside the liquid. Think about like a carbonated soda. The solubility of that carbonation is going to change dependent on temperature. If it gets too hot, the soda becomes flat because the carbonation comes out of the soda. Then the last thing that we can talk about, again, focusing on gases, is pressure. Pressure actually only affects gases because only gases are compressible. Think back to your gas laws. So there's actually something called Henry's law that describes the effect of pressure on the solubility of gases. As we increase the pressure, we're going to basically be forcing more gas particles into solution. This is how people get sick scuba diving. When they come up too fast and get the bends, what happens is as they're at the higher pressure down at the low depths in the ocean, the pressure pushes more gas into their blood. If they come out too fast, come up too fast, the pressure drops and the gases are trying to come out of solution. But if you get too many gases coming out of solution in your blood, that's going to create lots of bubbling in your blood. Obviously not a good thing. And so that's where people get sick from that. So we've got pressure, temperature, and the identity of the substance or nature of the substance. These are going to affect how much or if things will be soluble. This is different from our list before where we were looking at the rate of solubility, the rate of dissolution. This is how much will dissolve. That was how fast things dissolve. All right, the last thing that I want to look at today is something called a solubility curve. So this is basically going to show the relationship of temperature to the solubility of the substance. So we have temperature on the x-axis and solubility on the y-axis. Now the y-axis is interesting. What it shows me is how many grams of the solute would dissolve in 100 grams of H2O. You may also see this as 100 milliliters of H2O, which is really the same thing since the density of water is 1 gram per milliliter. I've also seen 100 cubic centimeters, which again is the same as a milliliter. So watch the units here, that a gram for water is equal to a cubic centimeter or a milliliter, and cubic centimeters and milliliters are equal to each other for any substance. So we want to know how much stuff can dissolve in 100 milliliters or grams of water. There will be a line, and on this line you're going to be able to tell what the solubility is. So say the temperature is 100 degrees, I can look at where the line hits and read that, oh, 150 grams of my solute would be able to dissolve in 100 milliliters of water. So we're going to be able to predict how much stuff can dissolve. And then if I'm under the line, if I have less solute than it could have, then that would be my unsaturated solution. Whereas if it turns out I have more dissolved than I'm supposed to have, that would be my supersaturated solution. So the saturated solution is when you hit the solubility exactly, and then above or below you have the unsaturated versus the supersaturated. Let's look at a couple problems and see how the solubility curve can be useful. In this question, we're looking for how many grams of the potassium nitrate can saturate 100 milliliters of water at 50 degrees Celsius. So we're looking for the grams of the solute, but it tells me what the temperature is. So I can read on the graph, and here's 40, here's 60, so I'm somewhere in between, about halfway in between. And I can read up to the line to tell how many grams would dissolve. I'm going to read over then so that I can predict how much would dissolve. If this is 50 and this is 100, I seem to be about 2/3 of the way down. So we would go maybe 80 grams of the KNO3. The other thing that you want to check is, did it ask the volume that you were given? 100 milliliters, 100 milliliters. And this where units can be confusing. If it asked for 100 milliliters, but over here it said per 100 grams, you need to know that that's the same thing. 100 grams equals 100 milliliters. If it asks for a different volume of water, then we're going to need to adjust our answer using a proportion. We'll get to one of those in just a minute. Let's try one more just using the graph first. Now we're looking for the temperature that can hold 200 grams and be considered saturated. So I'm going to find my 200 grams on the left now, and I'm going to read over from the 200 grams to my solubility line, and then I will go straight down in order to find the temperature. And it seems to be right in between 80 degrees Celsius and 100 degrees Celsius, so I would say 90 degrees Celsius, because it said the exact amount per 100 that I want to be saturated. So I'm reading the line. Let's try one that's a little bit trickier. This time it does tell me the temperature and asked for grams, very similar to the first question. But the thing that's different this time is that it asks for 500 cubic centimeters of water, which does not match up to my 100 milliliters of water. So I'm going to start by using the line like I did in the first one, where I say I'm at 100 degrees Celsius, read up, and read over. And so from the graph, I get that 250 grams of KNO3 can be dissolved in 100, and this says milliliters of H2O. So now I want to find a proportion where I'm solving for how much solute could go into 500 cubic centimeters of H2O. So to use a proportion, you need like units on top and like units on the bottom. Milliliter versus cubic centimeter shouldn't be left like that, but it doesn't really matter which one you change because 1 milliliter equals 100 cubic centimeters. So same thing. Basically, we have 5 times as much water. So if I have 250 grams of KNO3 per 100, how much do I have per 500? And we would have 5 times as much, or 1,250 grams of KNO3 per 500 cubic centimeters of water. 1,250. If it asked for less water, you could also end up cutting it in half too. So basically you're using your graph in order to find out the base number and then adjusting for the volume of water using a proportion. One last type of problem with this I want to go over. If we change the temperature, we can actually use the graph to predict how much will come out of solution. On our last question, I'm going to go ahead and give you what a real true solubility graph looks like. Usually there's not just one line on it. Usually they'll put multiple lines or show the solubility for multiple compounds. And so the idea is we've got to find the correct line, then use it to identify the information or solubility from the graph, and then see if we need to adjust the volumes. So first of all, what's our substance? KCl. So KCl is right here, meaning this is the line that I'm interested in. Only interested in that line, and for this question I can ignore all the other lines. I want to know what the solubility is for two different temperatures for this question, at 80 degrees and at 45 degrees. So let's go ahead and practice our line reading skills in order to get those amounts of solute. So at 80 degrees, if I read up to the line, I'm pretty much at this intersection of my 50 grams. So I'm going to note that off to the side. At 80 degrees Celsius, we have, 50 grams. Okay, the next temperature that I'm interested in is the 45. So that's about halfway between 40 and 50. If I read up, I'm pretty much at this line of 40. So at 45 degrees Celsius, I have 40 grams. So that's the information I need from the graph, but what do I really need to do to answer the question? The question's asking how much will precipitate. Precipitate means come out of solution. So if the solution can hold 50 grams at my first temperature and 40 grams at my second temperature, how much will it have to lose in order to stay saturated? We got to find the difference here. Subtract. 40 minus 50 is 10 grams. And then we want to usually include the substance, especially on a graph that has many of them. We would have 10 grams of potassium chloride coming out of solution if the temperature of the solution dropped from 80 degrees Celsius to 45 degrees Celsius. The last thing that you want to check is, was it for the right amount of volume? 100 cubic centimeters is equal to 100 cubic centimeters. It even looks the same on this example. If it were twice the volume, we would get twice the amount of substance out. So just always check at the end of the question, do I need to do a proportion to adjust for the volume? In this case, we don't. In this case, we have 10 grams that come out of solution. All right, guys, that'll wrap up solubility curves and everything that you need to know about your basic vocabulary for solubility. The next notes that we'll do are all about concentration. So we'll see you there.